So the videos that we're going to look at, if you want to reference them later, first of all, there's a list right here, and these slides will be up in our lab notes section. But for those of you who haven't been to our YouTube channel, I just wanted to go ahead and show you where you can find all of our videos. So this might be helpful while you're studying for the exam. So if you go to either the lecture notes or the video section, so I'm going to click on videos. And here, recordings of our lectures can be found here, so you're going to link right here. All right, so here are all our videos, and they are organized into playlists. And so what we're about to look at is Lab S, but you can see all the different chapters are here, and all the different labs are here. So we're going to take a look at this playlist. There's one that I have in here that's actually a great fun experiment, especially with little kids or the little kid inside of you. And that is doing chromatography with M&Ms and Skittles. So I'll leave that one for you guys to look at on your own if you're interested. Done this with little kids before, they absolutely love it. Done it with adults before, they absolutely love it. So just throwing this one in there for fun, but we will be taking a look at the other videos in here. And we are going to start off. Zoom is covering my controls here. There we go. No way, Zoom. There we go. All right. So we are going to start off with the solubility of alcohols. And what you're going to see in this video is just like we talked about up here. The water layer is going to be blue because it's got a little bit of blue food coloring in there. Okay, so what you just saw was water, an equal amount, added to each one of these test tubes, and then the food coloring. So this is your water or aqueous layer. And if you're not hearing any sound from the video, that's okay. There's actually not any sound to this video except for background noise. Oh, and it looks like they did use methanol, even though it's highly flammable. All right, so here was our water with food coloring. So again, the blue is just to show off the water. It is very nice. To the end here. All right, so now here are the test tubes, and unfortunately the little red bar at the bottom is covering the names. Let's see. There's a way for me to... even in full screen, it does cover the names a bit, but number 1 is your methanol, 2 is ethanol, 3 propanol, 4 butanol, 5 pentanol, 6 is hexanol. So let's go back and take a look at your lab now. All right, so here is the first page of the data sheet. And again, if you don't have this data sheet, just go ahead and write it on a piece of paper. And you're marking these as miscible, partially miscible, and immiscible. I'm gonna go ahead and get rid of this for a moment. All right, so right now what we're looking at is seeing if the alcohols are soluble in water. And the way you're going to determine if it's miscible, partially miscible, or immiscible is whether it is all one layer, that would be miscible. If it is two equal layers, then it is immiscible. And if you have two unequal layers, then you'll label it as partially miscible. So first off, any questions on how you're going to determine if it's miscible, immiscible, or partially miscible? So take a moment and fill into your data sheet, and all you need to look at is ethanol, which is number 2, propanol, which is number 3, butanol, which is number 4, and pentanol, which is number 5. So you are going to mark number 2 through 5, ethanol through pentanol, as either miscible, partially miscible, or immiscible. And again, the way you're going to determine the difference between partially miscible and immiscible is by comparing the dark blue layer to the top colorless layer. If they are approximately the same, then you'll call them immiscible. If you see that the alcohol layer, the layer on the top, is significantly smaller than the layer on the bottom, you'll call it partially miscible. So you're taking a moment and you're filling in that data table. So 2 through 5, you're determining miscible, partially miscible, or immiscible. So we have a really good question about the color differences that you see in ethanol. You also see a similar one in methanol, and the only reason there's a color difference is they haven't stirred it. So yes, they should have stirred it or shaken it. If they were to do that, then I would agree that it's miscible. So because there's no distinct layer, it is definitely miscible. Good question. Ben is saying that he doesn't see any partially miscibles, and I would agree with that. If you compare the top here to the bottom for 4, 5, and 6, they all look pretty immiscible to me. And it looks like Jessica came to the same conclusion. All right, so next up, I want to talk briefly about the solubility in hexane. So I couldn't find a good video for this, and the reason is that nobody really put one out because all of these have a carbon tail, even if it's pretty small. And what that means is with that nonpolar hydrophobic end, all of them go very well into hexane. So hexane is a nonpolar solvent, and so every one of these is miscible in hexane because of that nonpolar end that they all have. So if we model the alcohols again as something like so, even if it has a short tail to it, this is nonpolar. And that is why it's going to be mixing perfectly with hexane, which is also nonpolar. So any questions about that solubility in hexane? Okay, any questions about the solubilities of alcohols at all? All right, so next up we're going to talk about extractions. So extractions can happen when you have a molecule that can dissolve in both water and a nonpolar solvent. And we actually saw some of those up here. So for instance, for ethanol, did you find that to be miscible, partially miscible, or immiscible? For ethanol. So is ethanol miscible, immiscible, or partially miscible? All right, so I'm seeing a little bit of both miscible and partially miscible. I'm going to call ethanol miscible, and the reason you're seeing a tiny little bit of a layer there is just because it hasn't been stirred here. In this video, they should have stirred or shaken it. So ethanol is an example of something that could mix very well, essentially perfectly in water. It could also mix perfectly in hexane, and we have a lot of molecules that can do that. They can go into either a nonpolar or a polar solvent very well. But the question is, does it do better in one over the other? does it essentially have lower energy, and is it more favorable to be in one of these instead of the other? And what we're going to be looking at is iodine. So iodine is a molecule that should be nonpolar. So if you were to draw its Lewis structure, iodine looks like so. And everything we learned about symmetry would say, hey, that is nonpolar. If you look up its dipole moment, it's going to say, hey, that's a dipole moment of 0. And we talked about dipole moments way back when, and I said this is a numerical measure of how polar something is. So my very bad joke was two molecules are sitting at Starbucks, and one was like, hey, I'm so polar. The other one is like, no way, I'm more polar than you. And the only way they can determine who's the most polar is to compare their dipoles. But a dipole of 0 means it's nonpolar. So here we see iodine. Iodine is nonpolar, or is supposed to be nonpolar, has a dipole of 0. However, it's highly polarizable. So due to its large size. So what do I mean when I say something is highly polarizable? Anybody remember what polarizable might mean? I see high charge, and that's sort of it. It has to do a little bit with something else, something that happens in London dispersion forces. Yes, the electron cloud swings more. It can easily shift its electrons, exactly, and it can create a temporary dipole. Because iodine is so large, it's really good at shifting those electrons from side to side. But Andrew, you are correct. Once it swings it to one side, it has a higher partial charge than something that's smaller and cannot swing those electrons. So Andrew, you were on the right track. But when we think of polarizable, we do think of those electrons swinging to one side or swinging to the other. It has to do with the size of the molecule and the number of electrons it has. So when it swings those electrons to one side, that becomes partially negative, and the other side becomes partially positive. And we talked in class about how when that happens to one molecule, the other one gets an induced dipole because it swings its electrons in response to the first one. Then they have an attraction, which we call the London dispersion force. So iodine, which is supposed to be nonpolar, sometimes doesn't act nonpolar because it is so polarizable. So iodine is extremely attracted to nonpolar solvents, but it can also dissolve into water because of its London dispersion forces. So iodine is another molecule like ethanol that could go into a nonpolar solvent, something like hexane, but it can also go into something like water. So we're going to take a look at a video, and in addition to the lab question, we're going to ask we're going to answer the question, which is a better solvent for iodine, a nonpolar solvent like hexane or a polar solvent like water. And in the video, they're going to use cyclohexane, which is very similar. Cyclo means this organic molecule is in a ring rather than in a straight line, but it's a very similar solvent, either hexane or cyclohexane. So let's go ahead and take a look at this video. And this one does have sound, so if you can't hear it, please let me know.
Something valuable gets thrown away, you should label all of your phases. So you can see here I have the aqueous phase labeled, and I'll have an organic phase that is labeled. Again, don't throw anything away until your product is isolated. All right. I'm going to add some of the iodine in the water to the separatory funnel. The rule of thumb is that the phase you're extracting, in this case is the aqueous phase, is about 2/3 of the separatory funnel, and the solvent you're going to use should be about 1/3. Now, another really important piece of data you want to have before coming to lab and doing an extraction are the densities. We all know the density of water is approximately 1, and then the density of the organic phase, which is cyclohexane, I'm going to use is 0.774. So what does that mean? It means it's going to be less dense than water, and it should be the top phase of my extraction. So I'm going to add, this would be my extracting solvent, in about 1/3 of the volume. Right? You can see my stopcock is secure, nothing's leaking out. All right, now to perform the actual extraction where I want to transfer the iodine to the organic phase. So this is a definition of extraction, transfer of a solute from one phase to another. So I'm going to place the lightly greased stopcock on top, give it a tiny little twist to make sure it's sealed, and carefully lift the separatory funnel off the ring stand. You want to slowly do an inversion as the first step, and it's best to use your index finger. If you're right-handed, you use your right index finger. If you're left-handed, you use the left. And pointing the end away from you, gently tip it and open the stopcock to release any pressure that might develop with dissolution of the two phases, or as we'll see in the next video, any gas that might be formed. You close the stopcock, and now it's really important to mix the phases. So you give it a little shake, open the stopcock, shake it again, open the stopcock again, and I'm really going to mix the layers, give it a good shake. Vent it one more time before inverting it and swirling it and placing it gently back in the ring stand. Again, make sure you don't knock the stopcock as you're placing it back in the iron ring so that it opens and your liquids spill onto the bench top.
All right, so this is a great video. It is showing a sort of a more advanced extraction than the one that we would do in class, but still a great video. So let's go back to the beginning. All right, so let me flip back to first. I'm going here to our data sheet. I'm going to move this out of our way. And the first thing I want you to fill in is what is the color of the aqueous iodine solution. So that is on your screen right now. So write down what color you see. Everybody's going to see that slightly different. Some people call it an orangish, a yellowish, a gold color. But write down the color that you see. So this is the color of the aqueous iodine solution. So this is what iodine looks like in an aqueous water-based solution. And in fact, we use iodine all the time in aqueous solutions. If you ever use betadine, that is an aqueous iodine solution. So they paint that on you sometimes before surgery. Sometimes when you get your ears pierced, they will paint that on you. They used to make little pads like alcohol swabs, but they would make betadine swabs, and that would have that iodine on there as well. So most of us, if you've ever had those, ever used the swabs, or if you've ever had surgery and they painted it on you, you know it's sort of a brownish color, and it tends to leave on your skin. You got to wash it off quite well because it will leave a little discoloration for a little while. But go ahead and write down the color that you see on the screen. So some of you might see that as brown, some of you might see it as orange or kind of a gold color. All right, any questions so far about this aqueous iodine solution? So the first thing we have is iodine just dissolved into water. All right, so next up, what I want to do is forward to, oops, I have a Band-Aid on my finger, so it's tougher to use my trackpad right now. Let's see, so there we go. So again, she's doing this in a separatory funnel, something we lovingly call a SEP funnel. You would have done this in a test tube. You would have taken equal amounts of your iodine solution, which we would have had already prepared for you, because it is a little tough to get the iodine into water. And then you would have added not hexane, but you would have added, kerosene. Kerosene is a little bit smelly, same kind of kerosene that you would use in a kerosene lamp. So hexane is kind of a nicer solvent to use. But here she's got her cyclohexane, and she's got that up on the top, and then she has her aqueous layer on the bottom. And she mentioned the densities. So she said the water has a density of 1, and your hexane and your toluene as well have a density of about 0.7. Or I should say the kerosene as well have a density of about 0.7. So the reason that the water layer is on the bottom is because it is more dense. So when you're in organic chemistry, this becomes a really big issue because some of the organic layers are on the bottom, sometimes they're on the top, just depending on their density. So you always have to keep an eye on the density of your solvent so you know which layer is on the top and which layer is on the bottom. And something very important she mentioned at the beginning, and not important necessarily in our lab, but it would have been important if you were in an organic lab. And that is you never throw away a layer until you are absolutely sure you've got what you need. And that is because it's extremely common when organic students are doing a lab like this for them to mix up their densities. And so they might think, hey, this is my organic layer in the bottom, I'm going to save that. And this is aqueous on the top, I'm going to get rid of that. And so they've done this huge lab, maybe they put 3+ hours into it, and then they're like, oh man, my product's in the waste container, or my product went down the drain because they threw away the wrong layer. So once you get to organic chemistry, for those of you moving on, I highly, highly recommend that you never throw anything away until you're absolutely sure you don't need it. And that's what she was talking about at the very beginning. All right, so now here we have, again, our aqueous at the bottom, and we have our organic layer up at the top. Oops, not where I wanted to go. There we go. All right, so here, and I'm only going to have you do the test tube here on the left. And normally in class, I would have colored pens and pencils for you, but go ahead and you can just write in what colors you see and where they are. So for your top layer, write in whatever color you think that is for the top here. And this is pretty colorless, but it might be a slight yellow here. And you can see that slight, you can write colorless or slight yellow or whatever color you see down at the bottom. So feel free to just write the name of the colors. Those of you who happen to have, a colored pen on you, go ahead and color. But all you need to do is write the names of the colors. Yes, I like coloring too. Actually, a lot of students love this lab because we break out the markers and the colored pencils, and people will just have a lot of fun with our very last lab. All right, so I'm not going to require you to do the one on the right, again, because I couldn't find a video for it. But in lab, it's really nice to see the comparison. So methylene blue is a polar molecule, and it does stay down into the aqueous layer. So what it would look like, and you're not required to do this, is it would look like we have that blue down at the bottom, and even after we shake, 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 it stays down at the bottom. Because it is polar, it has no attraction whatsoever to the organic layer. So for both of these, we have our aqueous down at the bottom, and we have our organic, which is nonpolar, up at the top. But again, you do not have to do this one on the left. I was just showing you what it would have looked like. So any questions on anything here? Okay. And again, you do not have to color this, so if you just wrote in the names, perfectly fine. Just to show you, she goes on in this video, in case you're like, oh, that was so much fun, I want to see the rest of the video. She goes on to do multiple extractions, and the reason is every time you do an extraction, you don't get everything out. You only get most of it out. So she's going to go on to do more extractions of the very same one. So here she is shaking again. And now when I see a comment in the comment box that mentions that it was lavender, and now we can really see more of a pinkish lavender color. So iodine is very interesting that it changes colors depending on whether it's an aqueous or organic solvent. So in the aqueous, it's that brown, and again, if you've ever had it painted on you in surgery, it's very brown. But once it gets into an organic layer, you can see it turning this beautiful purple, and you can see the aqueous layer getting clearer and clearer. And there it is again. And now what she's doing is she's slowly letting out one layer at a time, and that's why we use the SEP funnel so that we can separate it. So it's called a separation funnel so that we can separate two different liquids. So it is a great video if you ever want to go back and you're feeling nostalgic about our very cool chemistry class. All right, so that was our extractions. Any questions about those extractions so far? Yes, so I see a question, is the aqueous layer always polar? And the answer is yes, because water is polar, so the aqueous layer will always be polar. So what that means is if you have something that is better off in polar solvent, it is more attracted to a polar solvent, you will then be able to pull it into the aqueous layer. So in organic chemistry, sometimes how they do that is they deprotonate, they remove a hydrogen, and then suddenly their compound is no longer a molecule, now it's an ion. Then they can do an extraction into the aqueous layer. Yeah. But yes, aqueous will always be polar. Now just to, oops, I realize I'm not projecting it. Just to answer the question that I had put up on the screen before, which solvent is better for iodine? Is it going to be a nonpolar solvent like hexane or water? The better solvent is the one that the iodine itself chose. So when you put aqueous and an organic nonpolar solvent together, you shake it up, this molecule will go to the place that is best for it. So the fact that iodine traveled to the organic layer tells us that the nonpolar solvent is the right one. So iodine is primarily nonpolar. It only has weak London dispersion forces. And that's why it's actually tough to get that iodine into water. So our lab tech does that for us. Same lab tech who's going to get your stuff out of your lab lockers for you if you left it there. But it's not easy to get that iodine into solution, into aqueous solution. Very easy to get it into a nonpolar solvent. So any questions about anything we've talked about so far? All right, so next up is chromatography. And I'm going to jump straight into the video because I think it's easier to see what's going on rather than for me to explain. All right, so again, if you can't hear the sound, please let me know.
This is paper chromatography to analyse the inks in Baro ink. I've cut a piece of filter paper to fit the beaker, and I've drawn a line about 10 millimetres up. I've also made developing solvent, which is made from 20 centimetres cubed of water, 20 centimetres cubed of ethanol, and 60 centimetres cubed of butanol. Draw dots of Baro on the line. Place the filter paper in a beaker and fill it up with developing solvent so it is just below the line. You don't want to touch the inks with the solvent. You then leave it for about half an hour to let the liquid move up the paper and watch the solutes spread. As you can see, the solutes have now spread according to their solubility in the solvents, and you're beginning to get different colours emerging. So you're getting pinks out of the reds, yellows and greens out of the blue, and purples out of the black. This is the same thing, but instead we've used felt tips to see if we get a greater range of colours. Right, we've now let this run for about half an hour. As you can see, the colours have spread out according to their solubilities in the solvent. We have blue, black, green, red. You can try this with other things that are soluble like this, other inks, and you can also do thin layer chromatography. Blue, black.
All right, so let's take a look at this one, and it is really fun. So those of you who are looking for just a fun afternoon activity to do, I highly recommend try the M&M's or Skittles chromatography. For that paper, you can use a coffee filter. For your solvent, you can use just salt water. So take some regular water, add some salt to it. It works really well. And it's really interesting to see the colors that are essentially hiding inside. So what you're actually looking at is the chemicals that make up those colors. So when you look at the back of the package and it says, hey, there's red number, whatever, 32, I don't know all the numbers for the different colors. All those different colors, though, they spread out and you can see them here. So chromatography is a way of separating out the different molecules that are inside of a compound, or I should say inside of a mixture. So to your eye, you might say, hey, that was just black ink. But the black ink, you'll see it separated into a red right here and a blue right over here and so on. And our green had some yellows and some blues. The idea is, depending on what your solvent is, some of the molecules will be more attracted to it and some will be less attracted to it. So the molecules that are very attracted to it are going to run faster up towards where that solvent's going. The ones that aren't very attracted will go very slowly. So if you were to do this, you always want to make sure that these dots of your pen are always above the liquid, and that's why they, in this case, have hung it above. The other thing you can do is if you have something stiff, like a stiffer piece of coffee filter, you can sit it in there as long as the original dots are always above your solution. But they do run up here, and there's a couple uses of these. And I actually talked to someone who used to manage a crime lab, a forensic CSI lab, and he was talking about how this is actually a technique they can use to verify if a certain pen is a pen involved in a crime. So, for instance, let's say you have a ransom note, and they find a pen, and they think, hey, I think this was the pen used in the ransom note. We've got a fingerprint on it, but now we got to verify that this pen really was the pen from the ransom note. What you would do is take a piece of the ransom note itself and do chromatography for it. And then on another piece of paper, you're going to take a mark from the pen that you think was the one that created that ransom note, and you will do chromatography from it as well. Then you will calculate something we're going to call an RF value, and I'll show you a video on that. If the RF values match, that could potentially be the pen that was involved in the ransom note. If they do not, you can rule out that pen. So it doesn't say for sure that this was the right pen, but it will allow you to rule out a pen. If we were in class, what I would have had you do is take two pens of the same color. So let's say two blacks, maybe two reds, but they would be from different brands. So we have Crayola and Crazy Art in the class, just to let you know that you missed out on playing with Crazy Art. And what you're going to see is they use very different mixtures of chemicals. So they will look very, very different in their chromatography. And that's how you can tell, hey, this pen that we found looks nothing like the ink from the ransom note, so this couldn't possibly be our pen that was used. So any fingerprints we got from this pen, they don't matter because this is not the right pen. So another place this is used is actually in your organic chemistry reactions. So a lot of time when you do an organic chemistry reaction, you're going to let reflux for a certain amount of time. And so refluxing is sort of like boiling. And so let's say you're going to let it reflux for 45 minutes. It'd be nice to say, hey, the timer's done, time to eat, right? That's how we do it when we're cooking. We're like, timer went off, I can take it out of the oven. Or maybe you stick a little toothpick in there to see if it's done. Well, in chemistry, our little toothpick is chromatography. So what you would have is this chromatography paper, but it would be a special type. It's actually on glass, and we buy it in actually these large pieces of glass, and it's got a special coating, and then we take a glass cutter to slice it up into something right about this size, And just like you see here, we have a line that we draw. We put it into a beaker that's got a solvent down here. And then we take some kind of a spotter. And normally your spotter is, it's a little capillary, very similar to what they would collect your blood with. And you put just a tiny little bit of the solution that is inside of your reaction mixture. So you put a little spot of that right here, and then you let this develop. Interestingly, many of our organic chemicals, you cannot see them except under UV light. So then you would use UV light to see your spots. If you see multiple spots, you may still have reactants that have not finished reacting. So you calculate their RF values, and you can actually look up what chemicals are inside of there. And that's a way that you can verify your experiment's done, because for most organic chemistry experiments, you want to make sure there's no more reactants left. So if you were to see, say, here it's like yellow and blue, but if you were in the UV light,
Green.
oops, if you were in the UV light, you see a spot here, and then a spot up here. You might look at that and go, oh my gosh, I know this isn't ready yet, but then you might calculate your RF value, look it up for these spots to verify that that's really what it is. Sometimes what you'll find is that you have an impurity. So you find an RF value that doesn't belong there at all, and then you're like, man, something's wrong in my mixture. But it's used all the time in organic chemistry to verify what's actually in your solution. All right, so what I'd like you to do is take a moment, and again, it's okay if you don't have colored pencils. Just go ahead and draw some kind of circles here to indicate what you see on the screen here. So for the blue marker, it looks like we have this kind of streak of purplish blue. Down for the second one, it looks like we have sort of a red, and then we have sort of a blue on top. And then here for the green, it looks like we got some yellow and blue. And then for our red, looks like we have sort of a fireball of red, maybe a tiny bit of yellow in there. So what you're doing right over here is you're drawing what you see. Let me get this back over here. All right, so you are drawing what you see on the screen there. And again, it's okay if you do all in one color. It's okay if you do pencil or pen. Just go ahead and do just a basic sketch, and then just write the name of the color next to it. And if you see it as a different color because you have some color differences, that's perfectly fine. So if you don't see red here, you see something different, that's okay. Write down whatever you see. So you're just basically sketching out this area right here, maybe one big circle around there. You're doing a very basic sketch here. Little sketch of this right here. Oops. Put this back up. Looks like we have a couple yellow spots, and then this big blue, and then it looks like we have this giant red with maybe a tiny bit of yellow in there. So doing just a basic sketch, and then writing down the color that you see, and again, it's whatever you see. So if I said it was blue, but you see it as green, you write down green. The idea is if we were doing this in a lab and you were to repeat your experiment, you don't want a color that you don't see. So if you wrote down blue, but you really see this green, next time you repeat the experiment, you might think something's wrong. So you always write down the color that you see. By the way, for those of you who are doing it on the data sheet, note that I crossed out solvent because we're not using the standard solvent that we would use in class. Don't worry about that, just do the sketch here. Yes, so I see a question coming in where you have the colors on our paper, we put the color that we see. Yes, so I want you just to kind of, you can draw a circle or an ellipse or whatever, and then write down what color you see. Draw maybe a circle over here or an ellipse, and then write down what color you see, and so on. So just a really basic sketch. It doesn't have to be perfect. You know, if I was doing the sketch, it wouldn't be. So let me show you, like for me, it would be something like, and then I would write down that to me this kind of looks purple. And then I might say, and I'm using colors, but you don't have to, I might say that I have here with some yellow in there. So something like so, and then just label those colors. So something like that. By the way, anybody who wants to be sort of a local celebrity to little kids, once we all get back to school, One of my friends who's now retired and used to teach chemistry, she goes to her grandkids' elementary school and she is Grandma Science. And she brings in stuff and they do little experiments like this and they get so excited whenever they see her. Sometimes she's just going back to school to pick up her grandkids and everybody's like, Grandma Science, Grandma Science. So this is a lot of fun. So if you're ever thinking, hey, I just like to do this with little kids, I don't have any of my own, but I'd like to do some with somebody else's little kids, the elementary schools would just love it if you came by and did something like this with their kids. And I'm sure it would look awesome on your resume as well. By the way, little kids love college students. They are so impressed with you guys. When instructors go out, it's like, oh, okay, it's like a lesson. But when college students go out, they just fall in love with you guys. I've taken students to like daycares and things to do this, and the little kids just absolutely love you guys. You know, you could probably even do it over Zoom. You could call the local elementary school or junior high and see if they want you to do a demo over Zoom. They would love, the kids would love that. All right. So any questions about what we did so far in terms of this chromatogram? Okay, so I'm not going to make you calculate the RF values, but I do want to show you how you would calculate these. That's because those of you going on to organic, this is going to be really important and you're going to do it frequently. And these RF values that you calculate, they are known values that you can look up. So if you see a spot you don't recognize, you calculate that RF value, you can go and you can look that up, and then you can find out what that thing is in your reaction, if it's a contaminant, if it's some reactant that hasn't reacted properly, if it is a side product. It's a product that shouldn't be in there. And if you're doing research, that's always really important. Like, hey, did I create something new? Do I get my Nobel Prize? No, but it's always really important to know what's inside of your reaction. So I'm going to show you a video on calculating RF values.
Today you guys had an opportunity to take all the different color black inks and use the control that you created to figure out what the ransom note was written with, which pen the ransom note was written with. And then you had to take a couple samples home from your control today, and I asked you to calculate something called an RF value. And an RF value is actually what's called a retention factor value. And the way that you go about doing that is very simple, actually. You're going to basically define the RF value. You're going to divide the distance the color pigment traveled by the total distance your solvent, which in this case we used water, traveled. And you can use millimeters or centimeters for either of these. So for instance, what I want to do right now is I want to find out, let's take a look at this sample. Let's use sample 3. I'm going to find out what the total distance of the water was. So if I take my ruler here, and I'm going to use centimeters, and I go from the very bottom, right where the dot was at, and I can try to kind of hit it right in the middle there, all the way up to where the water traveled. I know you probably can't see it, but if you look really close, there's actually kind of a dingy orange line where the water ended, and I drew a little mark there. So if I take my ruler and I look, I'm right about maybe at 61, 59, 58. So with this, I will actually go with 61 on this one. So the distance that the water traveled, 61 millimeters. And I'm going to go and figure out what the very first color RF value is. And so if I look, you'll see I see four colors. I see a yellow, a blue, a dark purple, and a light purple. So I have 4 colors that I'm going to find RF values for. So I'm going to actually, you'll see that some videos tell you to measure it right from the center of the color. So kind of right in there, maybe right in there, right in there. We're going to go from the tops of our color. So I'm going to take and measure from the bottom to the top of the yellow, and it looks like I'm kind of hitting right around right here, and that's taking me right about 23, maybe 22 millimeters. So 22 millimeters, that's going to give me 22 divided by 61. It's going to give me a ratio, and I'm going to use 2 sig figs here. It's going to give me 0.36. So 0.36 is going to be the RF value for my yellow pigment. And I want to do the same thing for the blue, the dark purple, and the purple, at least for this sample right here. Okay? So I hope that helps, and tomorrow I'll see you with the different color.
All right, so again, I'm not going to have you fill this out, but just give an idea of what you would have done. And what I would have asked you to do is here you would have, say, 2 different red markers or 2 different black markers. And within each one, you would see the different colors, and you would do exactly what that person in the video did, is you would measure the distance from the origin to the center of the spot. And as he mentioned we normally do go for the center of the spot, so like right here. So you would measure this distance, and here I have it measured at about 1.2 centimeters. He used millimeters, but you could easily use centimeters or another measurement as well. And then you would also measure from the origin to the solvent front. So that's as far up as your solvent reached. And here we have it measured at 6.1 centimeters. You would do the division, and that would be your RF value. So you would do that for every single color you would have seen in each marker. And I know it is a little tedious, and it's sometimes a little challenging because normally when you do this in a lab with the equipment we have, you do get something similar to what you saw in that video. Let me see if I can do this. It kind of streaks like he had it. Doesn't usually stay in this nice up and down format. But again, that's what you would have done, but I'm not going to make you do that. So I'm going to go ahead and cross that out. So what I need from you in terms of your lab is I need you to have part A filled out. So you're going to tell me if alcohol is miscible, partially miscible, or immiscible in both the water and the hexane. You're going to tell me before mixing what was the color of the iodine solution. You're going to have this left side filled out. You don't have to have the right side filled out. And again, you do not have to have the colors actually colored in, but you can just say what you see. So if you saw this as purple or pink or whatever color you saw, and then whatever color you saw down here, that's fine. And then for this part C, you have a basic sketch of the chromatogram that we saw in the video. Again, if you ever want to go back later and jump straight to this video without watching the long lab video that we're creating here, you go to the video section, and then you click the link here, and you can jump to our YouTube site, where we have so many fun chemistry videos. And then you can open up the playlist for Lab S, and then you can jump straight to these videos. My internet is, there it goes. So there you can jump straight to our Lab S. Watch all those videos in all their glory, and if you'd like to see the M&M's and Skittles video, it's a fun video, good stuff you can do at home. Alright, but that is the end of this Lab S, so I'm hoping that you get it turned in today, if not tomorrow. I would recommend just get this done, turn it in as soon as possible, and then you don't have to worry about it.